So what I was saying right at the end of the last video was that when you're building a curve, when you have to put a curve in, be it an exit ramp or whatever, and the space is limited, that then we bank the curve so that we're not just dependent upon the friction to allow you to go around the curve. And so on a bank curve, there's a component of the normal force that is pushing you towards the center, and that will help the component of the frictional force pushing you towards the center to allow you to go around the curve. Remember that to go around the curve, the centripetal force is mv squared over r. So if you can't make the curve big, your r is going to be tiny. And if your r is tiny, then this side is large, which means the centripetal force needs to be bigger. So that's, or you need to make your v smaller. So by banking the curve, we can make our centripetal force bigger by using a component of the normal force in the x direction to add to it. Okay, so if we go to, I'm just going to go back here and draw a new example, or a new picture. So here's my FG, and my FN is always perpendicular to the surface, so here's my normal force, and it's going to have an FNY and an FNX. So this is my FNX, this is my FNY. So like I said in the last video, and on a banked curve, it's the Fn we break up, not the Fg, and that's because we're not moving up and down the incline like we were when we used to tilt our axis for an inclined plane. We're driving along the, like on the incline at an angle. And so we need a force like the Fnx pushing us towards the center of this circle. Okay, so now when engineers do this, when they figure out, so a few minutes ago I said, so Fc is equal to mv squared over r. So when engineers are about to create an exit ramp or some kind of a curve, if they're building a highway, whatever they're doing, they look at, well, what's the speed of the area that this curve is going to be in? Because they don't want people to have to slow down too much. And then the second thing they look at is how much land do I have? So that exit ramp coming from the St. John Highway onto the Trans-Canada, coming back from St. John in the middle of nowhere, that circumference of that ramp is 1 kilometer. They didn't need to bank that. They had a huge amount of land, and so they didn't need to bank it. You could go at a fairly decent speed. I think it's 70 around there, because they had so much land they could make a big curve. But if it's an exit ramp in a city, then obviously they don't have that kind of land, so they're going to need to bank it. So let's take a look at the math. So when an engineer, and it's usually the civil engineers that do this, when they do this, when they figure out what angle to bank it at, they totally ignore friction. So they do it based on the slipperiest, iciest, grossest day out there, and they say, let's see what speed a person, or what angle it needs to be for a person to go around at the speed that would be good for this section based on the radius we can have. So just like all of our forces questions, we would start with some of the forces in the y direction, and in the y direction, the vehicle isn't moving. And so it would be Fny minus Fg will equal 0. And this theta down here will be this theta here. And so Fny is the adjacent side, so it'll be cosine. So it'll be Fn cos theta, and take the Fg over, will equal mg. So always we're looking for an expression for Fn, so Fn will be equal to mg divided by cos theta. Notice how this is different from when we were doing inclined planes, okay? We can, once you have that, then go to the sum of the forces in the x direction. And in the x direction, it's going to be equal to mv squared over r. It's the centripetal force. And when they're figuring this out, and they assume no friction, then in the x direction, it's Fnx only is equal to mv squared over r. And Fnx is the opposite side, so it's Fn sine theta. is equal to mv squared over r. And so now I can sub in for my Fn, and so it'll be mg over cos theta times sine theta will equal mv squared over r. So check it out, the m's will cancel, which is a great thing, because that means it'll work no matter what the mass of your vehicle is. Sine over cos is tan, so this will be g tan theta will equal to v squared over r. Bring your g over, so tan theta will equal v squared over gr. So if I know the speed I want, I know the radius based on the land I have, I can figure out what angle do I need to bank it at. So maybe let's go back and create an example here and do some numbers. So the first part of the example, the first part of a question will say, let's say a curve of radius 30 meters is perfectly banked for 40 kilometers per hour, which is 11.1 meters per second with the 1 repeating. When you see that phrase perfectly banked, it means the engineers did what we just did. They did the sum of the forces assuming no friction. Okay, so then we could go down here and we could get our angle. Tan theta is equal to 11.1 repeating meters per second, and you're going to square that, times 9.81 meters per second squared, and the radius I think I just said was 30 meters. And you'll find your angle. Don't forget to square the 11.1, do inverse tan, and in this case you'll get an angle of 22.7 degrees. So then the engineers would bank the curve with that. But in these questions there's usually a part B which says, so then what would the coefficient of friction need to be if you wanted to go around this curve at like 80 kilometers per hour, which would be 22.2 repeating if 40 is 11.1 meters per second. Okay, so now what they're saying here is you see that posted sign, and for a curve, you know, the yellow sign that says 40, and you go higher than it. Well, and you go higher than it on normal days. The only days that we probably pay attention to this sign and go at it or lower is probably when it's a dry or an icy, freezing rain, snowy day. Then we'll go lower, 40 or lower, and we'll worry about getting around the curve. But engineers who build highways know that. So they base it on when there's no friction, knowing that we'll probably go higher. So if we want to go at 22.2 meters per second around this curve, then we need friction. And so we need to go back up here and put our friction in. And it's going to have a component in the x direction that's going to help the centripetal force, and it's going to have a component in the y direction. So the first step in these questions will be to find the angle, and then the second step will be to find the coefficient. So now when you, that you want to go faster with. So you have to go back and redo the y, because now the Fn is not going to be the same, because you're going to have Fny going up, Fg still going down, and this time friction in the y direction going down. Fny we already figured out was Fn cos theta. Fg is mg, and this theta here is the same again, and y is sine. So this will be FFR sine theta is equal to 0. You're always trying to look for the an expression for Fn, but be careful here because friction has an Fn in it. So it'll be Fn cos theta minus mu Fn sine theta, and then take your mg to the other side because it doesn't have an Fn in it. Pull out your Fn, so you'll have cos theta minus mu sine theta is equal to mg, and so then Fn will equal mg over cos theta minus mu sine theta. Now, you're going to go to the x direction and do the sum of the forces in the x. Okay, so we have this. And when I run out of time here, you before you start the next video, just see if you can finish it. So it'll be sum of the forces in the x, and this time in the x it'll be Fx plus friction in the